Okay, I think we can get started. Welcome to the virtual symposium on construction on concrete innovation, vConcrete 22. So this is an idea that Nancy and Ahmed proposed, and I'm willing to play the Zoom host. So my name is Julie. I'm a professor of nuclear science engineering and material science engineering at MIT. And we have a lot of problem, like a lot of tasks ahead of us. There is the issue of CO2 emission reduction. We are now at 50, and we need to cut it down by 50% in 10 to 20 years. We have an ambition gap here. And also, if you look at the numbers, these numbers, 2 to 3 degrees, means we probably have to think about climate adaptation. So with a lot of changes in our infrastructure, with housing, etc. And faced with that, I have been organizing this MIT A+B Applied Energy Symposium, where A stands for action before 2040. And a lot of the technologies like solar, wind, and nuclear energies requires innovations in construction and concrete. And B is what happens after 2040, called beyond 2040 technologies. And that may involve a lot of the adaptation technologies. So in all these renewable energies, clean energy conversion, energy storage, for example, grid-scale batteries, mitigation technologies, transportation, food, water, etc. I mean, we all need innovations in concrete and constructions. And so I list for nuclear energy, the major, biggest issue is indeed in civil construction. So I classify them as type A, and we really need to get moving in the next decade, and application of robotics as well. So the fundamental problem is very concisely represented in this chart put out by McKinsey in 2017, where they compared the labor productivity in different sectors of the economy, starting from 1947. So everything is in 1947 dollars, if we will. And what's amazing is that in the oldest sort of production, which is agriculture, in the last 70 years, we had a 16-fold increase in labor productivity. And in manufacturing, in factories, there is 8.6 factor in labor productivity. The whole economy is 3.3 times more efficient compared to 1947. But if you look at construction, we're only 10% more efficient than we were in 1947. And in fact, if you look at this orange curve, after 1970, there is a gradual decline in construction labor productivity. And a very similar situation is mining. Now, both mining and construction are essential for the energy transition, for the challenge that we face ahead of us. And this is reflected in the nuclear industry, in the nuclear energy industry. So we have this plant of Vogtle in Georgia, which is severely delayed, and the cost has doubled. And this is one of the biggest limiting factors to nuclear energy, which in the 1970s have achieved the greatest decarbonization on Earth. But it's bogged down by this huge inefficiency in construction. So just to give you an idea, this is the breakdown of the percentage of cost in building the nuclear power plant. The nuclear power plant is very efficient to run, but the capital cost is the main issue. And out of these, only 12.6 come actually from nuclear specific equipment. And then most of the costs, such as yard, cooling, excavation, installation, engineering, procurement, construction costs, most of the costs have to do with the civil works in the civil engineering of this. And this is reflected in a 2018 MIT report on the future of nuclear energy in a carbon constrained world, put out by my colleague, Professor Jacopo Bongiorno, that we really need big innovations and productivity enhancements in construction. So the costs are dominated by civil works, by structures, by buildings, and a lot of the indirect costs associated with on-site work. So what could make a difference to nuclear energy? Well, one thing we have looked at is this steel plate composite, where it can save time in building, in pouring the concrete, as well as in ultra high strength concrete, where we can use less rebars and so forth. So there is actually a list of the things that in 2018 we saw, for example, automated pouring of concrete, functionalized concrete with fly ash, this steel plate composite, which actually achieved certification for nuclear construction in 2015, using ultra high strength concrete with silica fume and fly ash, which I know Nancy has worked on. And basically think about construction time and cost that really can be the game changer for large scale constructions, infrastructure projects. And since 2018, of course, there is this explosion of construction 3D printing. And so just last month, I think in Oman, I think there was this, the world's largest 3D printed system, which used real concrete instead of mortar. And it's really interesting to think about, how big can this go for nuclear. And we have also other, vanilla types of concrete degradation issues, like the alkali silica reaction, which is actually limiting the certification of old nuclear power plants. So these are $10 billion assets, and their relicensing, the renewal of their license from 40 to 60 years and even to 80 years will greatly delay the CO2 emission. But they have issues with aging of concrete, and also mid-level nuclear waste is stored in concrete casks, and a lot of the nuclear weapons waste are entombed in these big concrete structures, and we worry about all different kinds of degradations like carbonation, chloride, all kinds of accidental situations. And so this is really, I think, essential to the whole renewable energy transition and specifically the nuclear energy industry. So I really look forward to learning from this community. I will hand over the hosting to Ahmed, who would chair the next few sessions, and to Nancy, just to say that if you come in, please mute yourself. And when there's questions, please type in the chat your questions. And I think when there are, maybe less than 100 people, people can just unmute themselves. But when there's a lot of people, it's good to type in the questions, and then Ahmed and Nancy would ask the questions. And then the meeting just, it's going to be recorded and posted on YouTube. So you do want to watch out, for, a little bit on what you ask. And then with that, I'd like to have my dear colleague, Professor Oral, to give the next opening.
Thank you very much, Ju. It's a great pleasure to be here. I have been asked to make some brief remarks for opening of this impressive symposium. I am pleased to welcome everyone to the symposium, which is a meeting on concrete and construction innovations. I am a professor of civil and environmental engineering here at MIT, and I'm delighted to see our distinguished speakers and distinguished audience. Also great to see some friends and colleagues. The topic of our symposium is innovations in concrete and concrete construction. Concrete is a fascinating engineering material. It's the most used man-made material on Earth, and is most likely that it will continue to be this way in the future, perhaps with some significant further evolution. The evolution of concrete engineering and construction over the past decades, from both the material development and the application perspectives, has been really amazing. What used to be regarded as a simple traditional material has now emerged as one of the most sophisticated composite materials, with its dynamically changing and chemically complex material behavior and its innovative applications to major infrastructure construction worldwide. In a way, the field of concrete engineering and construction has become a source of inspiration for innovations and contributions to advanced engineering methods and technology developments. Concrete engineering and construction today face a grand challenge of Earth's sustainability in view of the current climate change crisis. The annual production of about 10 billion tons of concrete worldwide is responsible for about 8% of carbon emissions. This is a huge carbon footprint. The challenges to reduce this carbon footprint towards a net zero sustainability are many, presenting new opportunities for development of innovative engineering approaches and solutions. I would like to mention just a few and mention this in some brief categories. First, in the materials area, material design and manufacture, carbon capture and carbon usage in curing, advanced and alternative cementitious materials is a huge area with challenges. Usage of concrete for safe storing waste materials on Earth, perhaps with modified surface properties to be consistent with the concrete products, hydration products, such as post-consumer plastic and other wastes is an area. As mentioned, the 3D print technologies and construction automation, advanced numerical methods for additive manufacturing, multi-scale analysis from atomistic to macro scale, adoption of AI and machine learning strategies to material and system optimization. And finally, sensing and monitoring for efficient performance of physical systems and creative methods of crack and damage detection methods as a basis for rehabilitation. All these are closely related to the sustainability challenges. And these are only a few to mention. So in this exciting science-based engineering journey towards our goal, I predict there will be a space for innovations, for potentially disruptive and approaches, disruptive efforts and applications. This symposium could not be timelier from that point of view in bringing together today the outstanding researchers and engineers internationally to share their knowledge and current activities and to stimulate discussions and creativity for approaches towards global sustainability through concrete innovations. I would like to welcome you again and thank you for your presence and look forward to a productive meeting. And finally, I would like to congratulate the organizers for this impressive symposium and thank them for their efforts. Thank you.
Thank you so much, Professor Ola. This is a very good introduction.